I've always loved origami. Something about the way a single uncut sheet of paper can be intricately folded into a coherent shape, figure, or animal. I've always been obsessed. Meanwhile, I'd always also loved math. I viewed it more as an academic thing, but that still begged to change as I naturally came to see origami in a mathematical way. Cute crane, but let's shake things up. Take a square sheet of paper and fold it diagonally both ways. Then, carefully fold as to create a ring of folded squares around the center, alternating it in mountains and valleys. Once these seemingly crazy yet precise folds are done, squeeze the corners and fold the zigzag squares inward till everything is crushed together. Once you let go, bam, a hyperbolic paraboloid. Not gonna lie, when this first happened to me, I was like, what?
And then we have a little something called Sliceform Art, where basically you take a bunch of sheets of paper, make slits, and you slip them into each other until it makes a 3D shape, like a hyperbolic paraboloid. And in this case, compared to these beautiful hyperbolic paraboloids out of origami, here you can really intuitively see the 2D traces. But what if I don't want to use a template? What if I want to really integrate math and make it myself? So that's what we're going to do. We're going to try to make our own slice-form hyperbolic paraboloid from scratch with just calculations, where art meets math.
To paraphrase yours truly, we'll be exploring the construction of hyperbolic paraboloids with Sliceform Art into the world of aesthetic and mathematically practical geometry, embedded within contemporary sculpting and modern architecture. And on a more multivariable calculus level, such a form helps us visualize 2D traces. Using this chapter 13.6 knowledge, let's construct a hyperbolic paraboloid from scratch. Let's look at our mini model. We can see parabolic traces on both perpendicular axes. We can also see that it is bound by a square, creating right angles at the bottom of each trace. And finally, we can see that there are slips of paper sticking out to help the cross-hatching work. With that out of the way, let's get mathing. First up on the docket is writing the correct equation. When y is a random constant, the equation becomes the form of x squared equals z, an upward-facing parabola. But when x is the random constant, creating traces in the y direction, the equation creates the form negative y squared equals z. Thus, it looks a little something like this crude sketch here. Now, in the spirit of aesthetic grandeur, I want to make sure that the largest slices use as much of an 8.5 by 11 sheet of cardstock paper as possible. Thus, I'll use GeoGebra 3D and handwritten calculations to determine the best equation for the job. To start off, we'll just input the basic function. It gives the right vibe, but it's a bit too steep for us to practically craft a model. Thus, let's start thinking about a quadratic surface equation and its traces. We want both parabolic traces to be less steep. Alas, we need to make the x and y coefficients smaller. Let's experiment. Next, we'll shift the graph up so we can actually create a model with a square base. And after plenty of trial and error, we've come out with this equation. X squared over 5 minus y squared over 13 is equal to z minus 49 over 20. Seems kind of weird? Let me explain it. Looking back at our model, we can see the traces that are going in the y direction, which are the upward-facing parabolas, have the highest max point in the very center trace, the one that goes through the origin. Let's explore that trace. Here, the slice will be in the plane with the constant x equals 0. And since it's literally in the center of the surface, the slice here is genuinely at the origin, 0, 0, 0. Now, we shifted the graph up, so the origin is right at the midway bottom point of the paper, with a length up to the parabola's vertex of 49 over 20. Since we assume the length will be 11 for each of these slices, the point here will be at 5.5, 0, something, and the one over here on the left will be negative 5.5, 0, that same something. Let's go find that something. All we have to do is plug in our values into the equation, giving us z. And what do you know? Z turns out to be 8.5. That works really well here, obviously. And after some more math, which I'll show shortly, we can determine that all slices using this equation can fit being cut out of this 8.5 by 11 cardstock. This includes the max downward-facing parabola slices in the x direction, as shown here. And how many slices are we going to need in total? Thankfully, I whipped up a quick physical diagram. Each square is a unit, so you can see that every slice is going to be 11 inches in width. But remember the need to have slips sticking out on every slice? Thus, the actual intersections of these slips will only be in a 10 by 10 region with 0.5 inch excess on each. In other words, we'll need just 11 slices in each direction if we do one slice per one unit, at x and y equals the constants of 0, 1, 2, 3, 4, and 5. This will result in 22 slices in total, with double ups on everything except the two center slices that go through the origin. For clarification in the construction process, I named every slice. For instance, 0A refers to the tallest y direction slice I did on camera. Moving forward, we take these values and the equation back to the calculations drawing board to whip up every single value we're going to need. As you can see here on this sheet of paper, every slice gets the main points they need at the written constant and independent variable points of y or x equals 0, 1, 2, 3, 4, 5, and 5.5. Also, due to me wanting to use inches, I had to turn all decimals into a super informal fraction over 16, since, I don't know who came up with this, but foot-long rulers divide units into 16ths. I'll never understand. Oh, also, z over 2 ought to be calculated, since we need to cut those slits every unit halfway down the length of z. Now, if you're looking to emulate my process, I suggest you look at my step-by-step instructional guide, linked below and in the final project document. For sake of time, though, I'm going to move on to the construction now. In short, though this process took a handful of laborious hours, I created imaginary 2D graph planes on each sheet of paper, or each trace. The origin lied at the bottom midway point of every cardstock trace, meaning 5.5 units measured on my trusty Dare ruler. From there, since up refers to the z direction, I used all of my calculated values to carefully plot every point on each 0, 1, 2, 3, 4, 5 independent variable unit. As well, I also used these values to calculate the lengths of every slit needed. This required the z over 2 calculation. From there, it just required some sketching, some cutting, and a lot of rinsing and repeating. Here's me taking 5A and 2B together and testing to see if they slide into their corresponding slits. The magnitude of their slit lengths, or z over 2, ought to be exactly the same. But before I knew it, we were done! JK, I needed to double up on every slice except for the middle pieces, remember? So now we're done with the cutting and can move on to assembly. We're working with 22 pieces. To describe it briefly, my tactic for doing so was first getting 2 end pieces from the x direction slices and sticking all the y direction slices into them. Now we can semi-easily slip the remaining x direction pieces into the skeleton to bring you a beautiful, gigantic hyperbolic paraboloid.
It's a little bit flimsy, but I think it's pretty much done. A bigger and homemade version of this little guy.
As you can see from these stills, the parabola 2D traces are very clearly seen, and now we have an inevitably deeper understanding of them, thanks to calculating all 22 slices within this model. I have to admit my model wasn't perfect, symptomatic of my subpar measuring instruments. Ahem. Nonetheless, sliceform construction was an incredible avenue into the real fields of mathematical and artistic construction. For starters, this is the best method to see 2D traces in action, despite inevitably not showing the third z equals k hyperbolic trace. From hyperbolic paraboloids to ellipsoids to even toruses, Sliceform has got your back. This shape is also everywhere in contemporary sculpting work and in architecture. Ewan can tell you more about that in his project, but there's so many modern buildings utilizing hyperbolic paraboloids through roofs, primarily attributed to its natural rigidity through opposing diagonal tension. Clearly, math and art work together in tandem, helping us in the classroom and in the real world.